Now we go for question number 33. Very important question. It is a short note about electric field lines. Electric field lines. Okay. Listen now. Surrounding to every electric charge up to certain region, we have its own electric field. Correct? Fine. Electric field is a reality. It is not an imagination. It is really existing. How can we say that it is existing really? Because if electric field is there, then only it will generate electric force. Then only we will have some exhibition of electric effect. Practically we find that surrounding to any given charge in the neighborhood, if you bring another charge, then that another charge is either repelled or attracted. So if that another charge is free to move, it definitely moves. What does it show? Some electric effect. And if that electric effect is experienced by that another charge, you must say there must be some electric force exerted on that another charge. And if electric force is generated, then you know any natural force is generated by its respective force field. So at that time we have to say that definitely it must have been produced by electric field. Correct? But why is the electric field there? Because there is a charge. So surrounding to every charge, definitely electric field exists, which generates electric force, which produces electric effect, which can be demonstrated, which can be observed practically. Okay, fine. Now when we know that really electric field is existing surrounding to every charge, then why not to visualize that electric field? But how to visualize that electric field? How to see that field? Actually, field cannot be seen. Field cannot be seen. Its effect can be seen. Correct? But there was a scientist, Mr. Michael Faraday, who had thought over this problem very first time. He thought that if I want to visualize electric field, how can I do that? He wanted to have pictorial presentation of electric field. He wanted to show electric field in the diagram, and for that purpose he had drawn some curves very specifically, and those curves drawn very specifically by Mr. Michael Faraday are only known as electric field lines. What are they known as? Electric field lines. Why are electric field lines shown or imagined? Just to visualize electric field existing around electric charge. Fine. Remember, field is a reality, but field lines are imaginary. Field is a reality, but field lines are imaginary. Why field lines are imaginary? Because even before Michael Faraday had drawn these curves, even before that, the charges had already electric field. So whether you draw those curves or you do not draw those curves, no problem. Irrespective of that, field is always present in the surrounding region to an electric charge. So I mean to say, whether you draw field lines or you do not draw, charge will definitely produce its electric field. Correct? Even before the birth of Michael Faraday, charges had their electric field, though electric field lines were not imagined, were not drawn. Correct? So I mean to say, field is a reality, field lines are imaginary. It is up to you whether to visualize that field or not to visualize. It is up to you whether to draw field lines or not. Correct? But when charges are there, they will definitely have electric field in the surrounding region. So field is a reality, field lines are quite imaginary. Correct? Fine. Now This is a very short introduction of electric field lines. It is not the definition. Okay, definition I am going to give in the same article. Look here now. We go for electric field lines of electric field of electric dipole. As shown in the diagram, you please consider an electric dipole. This is the positive charge of the dipole. This is the negative charge of the dipole. Remember definition of electric dipole: a system of two unlike point charges of equal magnitude separated by some finite distance is called an electric dipole. Remembered? Fine. Now, surrounding to this electric dipole, it has its own electric field. Now, we want to show that electric field using some specifically drawn curves called electric field lines. But how to draw those curves? I am showing you. You just select one point, say at this very position, say point P1, okay? And you just imagine a test charge placed at this point. How is the polarity of test charge? Customarily it is taken positive. So you may think of positive point charge placed over here. Fine. Now what this positive charge will do? Will repel this positive charge. And then what this negative charge will do? It will attract this positive charge. So if you place a test charge here, then one repulsive force is exerted this way, one attractive force is exerted this way, and then out of two forces you will have resultant Coulombian force, which is found to be in this direction. And don't you know, direction of electric field is nothing but direction of resultant Coulombian force, correct, exerted on a unit positive charge. So if the resultant Coulombian force is in this direction, meaning thereby at this very position the direction of electric field, say vector E1, must be in this direction. Now select another point, say point P2. Just place here test charge. Why we prefer to place test charge? Because we should take care that this charge distribution should not be disturbed. Okay? So think of placing a test charge at this very point. Fine. How is it? Positive. This positive charge will repel this positive charge. This negative charge will attract this positive charge. So one repulsive force is this way, another attractive force is this way. Then out of two forces you will get resultant Coulombian force, which is found to be in this direction. And direction of resultant Coulombian force exerted on a unit positive charge gives us direction of electric field, which is right now in this direction, say vector E2, correct? Similarly, you can find out direction of vector E3 at point P3. In the diagram, I have selected these points rather far away from each other, but you may take those points very close. If you are selecting the points very closely, say P1, P2, P3, P4, P5 like that, then after if you just draw a curve passing through those points, then that specifically drawn curve is only known as electric field line. Electric field line. Correct? Now how would you define it? I am showing you. A characteristic curve considered in the electric field, the tangent drawn at every point on which gives us direction of electric field at that very point is only known as electric field line. A characteristic curve considered in the electric field, the tangent drawn at every point on which gives us direction of electric field at that very point is only known as electric field line. Okay? Last time. A characteristic curve considered in the electric field, the tangent drawn at every point on which gives us direction of electric field at that very point is only known as electric field line. Okay, fine. Now, if you take point P1, say right from beginning over here, then you will get that electric field line like this, correct? But right from beginning, if you take point P1, say here, then P2, then P3, then you get electric field line like this, correct? Similarly, if you start from this point, you may get it this way. If you start it from this point, you will get it this way, like that. This is how you can prepare the entire electric field, which is shown here pictorially in the diagram using the help of electric field lines. Okay. Where is this figure drawn? On the blackboard surface, which is a two-dimensional space, which is a plane, correct? But actually this electric field is existing in three-dimensional space. So if you want to visualize that whole three-dimensional electric field, then you can just do one thing. Consider this as an electric dipole. Suppose here is negative charge, here is positive charge, and then you may take this axis of the dipole as axis of rotation, and then you may rotate this whole figure this way. You may rotate it, right? And if you rotate it, then it will just give you the electric field existing in the three-dimensional space surrounding to electric dipole, correct? You can very easily visualize that field. Fine. Now this electric field is said to be having some cylindrical symmetry. A point charge has spherical symmetry, and this electric dipole has cylindrical symmetry. Okay, fine. Now, after the introduction and explanation of electric field lines, I would like to show you some characteristics, some specialities, some peculiarities of electric field lines. Let us make a list of all these peculiarities. First, the starting and end of electric field line. You can see in the diagram, starting of electric field line takes place from positive charge and it is terminated at negative charge. It is originated from positive charge, terminated at negative charge. Okay? They are always from positive charge to negative charge. Fine. What about direction of tangent? On every electric field line, if we draw a tangent at any point, then that tangent definitely gives us direction of electric field. Remember that tangent gives only direction of electric field, not the magnitude, only direction, correct? Tangent drawn at every point on electric field line gives us direction of electric field at that very point. Fine. Here, closed loop is not formed by electric field line. Closed loop is not formed because every electric field line originates from positive charge getting terminated at negative charge. It does not form the closed loop, correct? Say, you may just make a round trip and you may argue, sir, closed loops are formed here. Suppose somebody is moving this way, look here this way, correct? Then he will be coming back to the same point. Then he will say electric field lines are making closed loops. No, it's not proper. You must move in the direction of arrow and then you must come back to the same starting point. If you can do that, then you can say electric field line forms closed loops. Here you can see when I am moving this way, I am moving in the direction of arrow. That is true, right? But if I now move this way, I am moving opposite to these arrows, correct? Then it is not the way to form a closed loop. Okay? So remember, for any stationary electric field lines never form closed loops. Electric field lines never intersect. Let us prove this result using method of contradiction. Suppose two electric field lines intersect at this very point. Suppose if these two electric field lines intersect at this point, then just now I told tangent drawn at every point on electric field line gives us direction of electric field. So if both these curves are electric field lines, I can draw two tangents at the same point. One tangent is vector E1 and it is drawn on this curve. Another tangent drawn at this point on this curve is this, correct? Then tell me, if these tangents are giving you direction of electric field, then it means to say at the same point, at the same time, electric field exists in two directions at a time. Not possible. At a given point of time, electric field can exist only in a particular unique direction. It cannot exist in both the directions simultaneously. It is very wrong. Okay. So conclusion is that no two electric field lines can ever intersect. Okay. Then we go for density, population of electric field lines. Why do we draw electric field lines? Just to show the presence of electric field pictorially, correct? That is true. But number wise, how many electric field lines should you draw? For that, customarily we have chosen one rule. What is that rule? Very simple. Wherever there is a very strong electric field, wherever there is a stronger electric field, we should show more number of electric field lines. Wherever there is a weaker electric field, we should show less number of electric field lines. So remember, number of electric field lines is to be shown in such a manner that it can give you measure of strength of electric field. Okay, I am showing you. Suppose we have non-uniform electric field. Here is the presence of non-uniform electric field, and in which you can see there is more crowding of electric field lines here, and here there is less crowding. You just do one thing. You select 2 points. Say here point P1 and here point P2. Correct? At both the points, what we do? We just consider a unit area chosen perpendicular to direction of electric field. This is also unit area. This is also unit area chosen perpendicular to electric field. Now tell me, here through this area, how many electric field lines are passing? 1, 2, 3, 4, 5, 6, 7. And here through the same measurement of area, only 3 electric field lines are passing. 1, 2, 3. Correct? Why it is like that? Because here electric field is weak and here electric field is strong. Okay. So remember one thing, number of electric field lines passing through unit area chosen perpendicularly to the electric field at any point is to be shown directly proportional to strength of electric field at that very point. I repeat, number of electric field lines passing through unit area chosen perpendicular to electric field is to be shown directly proportional to strength of electric field at that very point. If strength is greater, number should be shown greater. If strength is lesser, number should be shown lesser. Simple. Then we go for uniform electric field. For uniform electric field, you must show electric field lines in this manner. In this manner means all these field lines must be shown mutually parallel. Not only that, perpendicular distance between each two consecutive electric field lines must be shown same everywhere. Okay. When you have such a picture of electric field lines, It indicates uniform electric field. For uniform electric field lines are parallel. For non-uniform electric field lines are not parallel. Okay? Fine. Come on, my dears, we proceed further in chapter number 1. Let us see now question number 34. It is about showing the electric field around a pair of like charges of equal magnitude. How would you represent that electric field using electric field lines? That is what we have to show in the diagram. Look, when you draw this figure, please take care of certain points first. Because these two charges are of equal magnitude, then you must show same number of electric field lines surrounding to each charge. Here, surrounding to this charge, I have shown 11 field lines. How many? 11. You may choose that number, any number, no problem. But whatever number you are showing here, same number you must show here. Okay? And the pattern of showing the electric field lines must be like this. Okay? Second point. All these field lines, they originate from a positive charge. Correct? So they are originating this way, and for a positive charge, don't you know, its electric field is away from it. That's why these arrows are away from this positive charge. Similarly, here also. And last point, you must take care that you should not show any two field lines intersecting with each other, because you know no two field lines ever intersect. Okay? Keeping all these points in mind, you must draw this figure. If this charge would have been absent, then these field lines might have gone this way. Correct? But because of presence of this charge, this field line doesn't go this way. On the contrary, it bends this way. It bends this way. Okay? Similarly, in the absence of this charge, this field line might have gone this way. But in the presence of this charge, this field line is getting bent this way. Got it? Fine. Now we go for question number 35. It is very important short note regarding electric flux. What do you mean by electric flux? It is a scalar physical quantity. You can show it by this symbol, that is phi. Spelling is PHI. The pronunciation is phi. This is small phi and this is capital Phi. Okay? Now, after all, what is electric flux? I am showing you. To understand about electric flux associated with a given surface, you please consider at this moment some uniform electric field. Correct? At present, you just consider uniform electric field having intensity vector E everywhere. And you must have remembered how do we represent uniform electric field? By those electric field lines which are mutually parallel and the perpendicular separation between each two consecutive field lines must be same throughout the figure. Okay, fine. Now, in this uniform electric field, as shown in figure number 1, you just consider some plane surface which is arranged vertically, correct? Its inclination, its orientation, its arrangement is like this, in which we can see the plane surface is vertical. Fine. Now, in this situation, you can see 1, 2, 3, 4. How many field lines are passing through this surface? 4. Okay. Now, what we do? Same surface, we just make it incline this way. Correct? Fine. When we incline this way, then as shown in figure number 2, through the same area of the same surface, now in this inclination, only 2 field lines are passing. How many? Only 2. and still if you bend it this way, and ultimately if you make it horizontal, then in this horizontal arrangement you can see through this plane surface there is no electric field line which is passing through this plane surface, correct? Fine. So here number of electric field lines passing through this plane surface in this orientation is maximum, here it is less than maximum, and here it is 0, okay? Fine. Keeping this point in mind, we would like to have some measure of how many electric field lines are passing through a given plane surface, correct? Just to have measure of how many field lines are passing through a given surface, we have defined one scalar physical quantity called electric flux. As such, it is a mathematical concept, but we can give its a physical interpretation also. What is that physical interpretation? I am showing you. We have defined electric flux this way. It gives us measure of number of electric field lines passing through a given surface when it is subjected to external electric field. Okay? Fine. Mind well, simply it is not a number. If it is simply a number, then it should not have any unit. But this electric flux has some unit. So itself it is not simply a number, it is a measure of number of electric field lines passing through a given surface. If that number is greater, then we say more electric flux is linked with that surface, more electric flux is associated with the surface, and if that number is smaller, we say less electric flux is linked with the surface. Got it? So depending upon the number of electric field lines passing through a given surface, we can have measure of amount of electric flux. Greater is the number of electric field lines, greater is the electric flux. Smaller is the number of electric field lines passing through a given surface, smaller is the electric flux. Simple? Fine. Now, here we define one spatial vector called area vector, or sometimes we call it surface vector, shown by symbol vector capital A. It is such a vector which is always drawn perpendicular to plane of given surface element, always perpendicular to plane of given surface element, and its length is chosen directly proportional to measurement of area of that surface. Okay? Such a vector is called area vector or surface vector. For example, when you are talking about say this plane surface, correct? Suppose I arrange it vertically, and now I would like to draw its area vector. Then as I said, it must be drawn perpendicular to this plane like this, correct? What about length of this vector? Length of this vector is chosen directly proportional to measurement of area of this surface. Okay? Greater is the area, greater is the length of area vector. Got it? Like that. Now, for this inclination, we can draw one area vector like this, which is perpendicular to this. Fine. And as shown in this figure number 1, we can see here direction of vector A and vector E, both of them are in the same direction. Correct? Electric field is towards the right hand side this way, shown with the yellow color, vector E and vector A, both of them are in the same direction. Angle between two vectors in the same directions, it is theta equals to 0 degree. Correct? And at that time, maximum electric field lines are passing through the surface, meaning thereby maximum electric flux is associated with that surface. Fine. Here what happens? The inclination is like this, then area vector which is drawn perpendicular to the plane of the surface will be like this, and electric field is still the same, that is towards the right hand side. Now angle between vector A and vector E is this much, which is theta. Okay? At present this theta is greater than 0 but less than 90 degree. greater than 0 but less than 90 degree. Okay. At that time, two electric field lines are passing through this surface, and that electric flux is less than this flux and it is less than maximum. It is greater than 0 but less than maximum. Here electric flux passing through this surface is, come on, less than this maximum but greater than 0, because some electric flux is passing through this surface. Fine. Now what about this inclination? In this inclination, the surface has become horizontal. For horizontal surface, its area vector will be like this. When surface is like this, area vector will be like this. Correct? Vertical. Fine. So that area vector I have drawn here, and this is electric field vector. Correct? Now this angle is 90 degree, and at that time, when theta is 90 degree, at that time, not a single electric field line passing through this surface. And when not a single electric line passes through the surface, naturally its electric flux should be 0. Correct? So here electric flux is maximum, here electric flux is 0, and here electric flux is more than 0 but less than maximum. Fine. So keeping this point in mind, we should define electric flux by such a formula which can give values as per this diagram. Okay? Keeping all these points in mind, we have defined electric flux through this formula. Look at the formula. Phi equals to vector A dot vector E. Vector A dot vector E. What is vector A? Area vector. What is vector E? Electric field. And there is a dot product, which is also called scalar product. That's why electric flux is scalar physical quantity. Okay? Dot product between area vector for a given surface and the electric field existing at all the points on that surface is called electric flux associated with that surface. So electric flux associated with any surface is nothing but dot product between area vector for that surface and electric field existing on that surface. Okay? Fine. If it is vector A dot vector E, then you know from the basic definition of dot product from 11th standard, it is A E cos theta, where theta is angle between vector A and vector E. Okay? Now just check all these flux values using this formula. Can we get respective values or not? Just check it. In here theta was 0 degree, put it here, theta 0 degree, cos 0 is 1, 1 is maximum for cosine function, 1 into A into E, that is A into E, correct? But because here cosine value is maximum, then phi should be maximum. That's why I am writing here phi maximum. And really we find that maximum electric field lines are passing through this surface in this orientation. So we say electric flux is maximum. Correct? Fine. Here electric flux is less than maximum but greater than 0. Let us see whether we can get the same value using this formula or not. Here theta is more than 0 but less than 90 degree. If theta is 0 degree, cos 0 is 1, flux will be maximum. If theta is 90 degree, cos 90 is 0, flux will be 0. But theta is greater than 0 degree but less than 90 degree, at that time flux will be less than maximum but greater than 0. That's why I am writing here 0 less than phi maximum. Okay? Here flux is greater than 0 but less than maximum. What about here? Here we should get electric flux 0 because not a single electric field line is passing through this surface. Let us check. Come on, here theta angle between area vector and electric field is 90 degree. Put it here, theta equal to 90 degree, cos 90 is 0. So flux should be 0, phi equals to 0. And really we can see in the diagram phi is 0. Okay? So what I mean to say, whichever electric flux value you observe in the diagram, same flux values we are getting from this formula. Okay? Now what about SI unit of electric flux? Very simple. you go for writing SI units of electric field and area. What was SI unit of electric field? Newton upon Coulomb, correct? For area, meter square. For area, meter square. So altogether the SI unit of electric flux is now Newton into meter square upon Coulomb. Newton into meter square upon Coulomb. Let us see one more unit. What was the another unit of electric field? Last time I told one unit was Newton upon Coulomb, we have already used. Another unit was volt upon meter, volt upon meter. So unit of E is volt upon meter, for area it is meter square. So altogether it will be now volt into meter, okay. Don't say voltmeter, no, voltmeter is an instrument. Here we are speaking the unit. So you must say volt into meter, okay, fine. And once you know the unit, can't you find out dimensional formula? Yes, we can. I have not written here, but I can tell you. Come on, Newton. For Newton, what is the dimensional formula for force? M raised to 1, L raised to 1, T raised to minus 2. For meter square or for area, it is L raised to 2. And for Coulomb, that is for electric charge, A raised to 1, T raised to 1. Okay? And then you can simplify. Got it? Fine. Now we should go for general definition of electric flux. This definition we have given, but now we go for general definition of electric flux, which is applicable for any type of surface. Here the surface we had taken planar surface, flat, but not necessary that every time plane surface only exists in the electric field, not necessary. Inside the electric field you may have some curved surfaces also. So for that we should go for general definition of electric flux. I am showing you. Consider this as given curved surface, correct? The shape may be arbitrary. Arbitrary means at random, correct? Fine. That surface I am taking as S. Now here is some electric field. This is external electric field. These are the field lines for that, okay? Now when this surface is exposed to that external electric field, naturally out of many field lines, some field lines will pass through this surface also. And because some electric field lines are passing through this surface, we can say some electric flux is linked with that surface, which we want to find out. Fine. For that, you just do one thing, divide this entire surface area into extremely large number of extremely small area elements, correct? And one such extremely small area element I have shown here. Suppose it is jth element. Which one? What is order? Jth, like first, second, third. Say this is jth order area element. Okay, we call it sometimes surface element. It should be chosen that small, such that electric field at all the points on which can be taken almost constant, correct? That much should be small, the area element. And that electric field existing at all the points on this jth area element, I am taking by symbol vector Ej. Fine. What about area vector? Area vector is to be drawn always perpendicular to plane of area element. If plane of area element is like this, slightly inclined, then you may draw area vector like this, correct? Perpendicular to that. That's what I have drawn here, right? And it is the area vector for jth area element, so I am putting symbol vector delta Aj, correct? Now angle between these two I am taking as theta, correct? Now tell me, just now how did you define electric flux? By a dot product between area vector and electric field. Here area vector is vector delta Aj and electric field is vector Ej. Just take dot product between them, it will be called electric flux associated with this jth element. Which element? Jth area element. That's why I am giving the symbol phi j. you must write this J well below phi. Okay, fine. This J is called suffix. Now, this is the electric flux linked with only this area element, but we require to find out electric flux linked with entire surface, and that total electric flux I just show it by symbol phi. To find out that, what you should do, you should make addition of partial amounts of electric fluxes. Okay, fine. Electric flux is a scalar quantity, mind well. Okay, so don't say vector addition, don't say vector addition. Okay, fine. And that addition I am showing by symbol sigma, but you should carry out that addition such that you should include all such area elements, correct? Not a single area element should be left out. You must include all the area elements. Suppose totally there are n number of area elements, where n is a very large number. Okay? Then you should carry out this addition right from first order of the area element to the last order. Means J varies from 1 to n. From 1 to n. Okay? Fine. Now this sigma I have written as it is. But what is value of phi j? It is vector Ej dot vector delta Aj. Same thing I have written here. Now tell me, the electric flux found using this formula would be really very accurate, provided really this much electric field can be taken constant at all the points on the chosen area element. But in order to have constant electric field at all the points on the chosen area element, we require to reduce its size. We should make it as small as possible. Mathematically, we should find out this electric flux by taking this value of delta Aj extremely small, we should reduce it, we should make it smaller and smaller, mathematically tending to 0. When you make it tending to 0, then that area of area element would be very, very small, almost like a point, and at that time, at that very position, the strength of electric field can be taken almost constant, correct? So, in order to have accuracy in this result, we need to take this limit delta Aj tends to 0, correct? And when you take this limit, at that time, this summation results ultimately into this surface integration, because you are going to find out this addition over the given surface. That's why that addition is called, come on, surface integration. If you are finding some addition on some curve, it is called line integration. If you are finding some addition on a surface, we call it surface integration. That's why I am writing here S. Okay? And this is electric field, which I have written here vector E. This is area vector. In this limit, now area vector you must show by this symbol vector dA, correct? Dot product as it is. Fine. So, from this expression, we can define electric flux in a most general way like this. Electric flux linked with any surface is nothing but surface integration of electric field taken over that entire surface. I repeat, surface integration of electric field taken over the entire given surface gives us electric flux linked with that surface. Okay? Last time, surface integration of electric field taken over a given surface is called electric flux linked with that surface or associated with that surface. Okay? If chosen area element is flat, plane, then its area, suppose it is A, okay, and if it is taken perpendicular to uniform electric field, then that electric field is E. At that time, the electric flux is A into E, correct? When chosen area is flat, plane area, and it is perpendicular to uniform electric field, the electric flux is A into E. Let us see we can get the same result from this general definition or not. Simple. Integration as it is, what we can write inside? E dA cos theta, E dA cos theta. But when given plane surface is perpendicular to uniform electric field, the angle between vector and vector E, you can see it is 0 degree. So E dA cos 0 degree, cos 0 degree is 1, correct? And now it is integration E dA, but because of uniform electric field, value of E can be taken constant. So you can take it out of this symbol of integration. So E times integration dA, E times integration dA. But integration dA means what? Summation of areas of all the area elements chosen over given surface. Given surface is this, correct? And when you add areas of all the area elements over this entire surface, naturally you will get total area of this surface. If it is capital A, then here you will get E into integration dA, which is capital A. So E into A, E into A, E into A, correct? When you will find out electric flux using this formula, in the case when given surface is plane and kept perpendicular to uniform electric field. Whenever any plane surface is kept perpendicular to uniform electric field, at that time use this formula for finding electric flux, A into E. Simple? Fine. Now we go for question number 36. It is about very important law in physics. It is one of the fundamental laws in nature. It is Gauss law or Gauss theorem for static electricity. What is Gauss law for static electricity? Let us see. Let us obtain that law, and using that mathematical form, ultimately we will give the statement. Okay? Let us obtain this law. Consider a point charge, say small q, located at center of some spherical surface. Okay? Now this spherical surface is a closed surface, correct, which encloses this charge. Such a closed surface which encloses some charge is known as Gaussian surface. Gaussian surface. Whenever you want to apply Gauss law, at that time whichever closed surface you are choosing, it is called Gaussian surface. Fine. Now surrounding to this charge, it has its own electric field. If it is positive charge, its electric field is away from it. That's what I have shown here with the help of such electric field lines away from this positive charge. Fine. Now, because these electric field lines are passing through this closed surface, you can say there is some electric flux associated with this closed surface. That total electric flux is suppose phi, which I want to find out. Okay? Now phi equals to, just now we have obtained the final result, surface integration of electric field. That is integration vector E dot vector dA. Integration vector E dot vector dA. Come on, this integration as it is. Come on, according to basic definition of dot product, here E dA cos theta. What is theta? It is angle between electric field and area vector. Just consider some area element, say at this position. That extremely small area I have shown here. Let it be dA. What about area vector? It is to be drawn always perpendicular to plane of area element. And that perpendicular direction will be like this, correct? And remember one more thing, for any closed surface, area vector is to be drawn always perpendicularly outward. Perpendicularly outward. That's why I am showing direction of vector dA like this, correct? And in the same direction there is direction of electric field also, vector E. So because these two vectors are in the same direction, angle between them should be taken 0 degree. That's why I am writing here 0 degree. Got it? Cos 0 is 1. And so far magnitude of electric field is concerned, for a point charge, what was the formula for magnitude of electric field? KQ upon R square. KQ upon R square. K is constant, Q for a given charge value is constant upon R square. For this spherical surface, its radius is same at all the points. Whether you take this radius or this radius or this radius, all the radii are same. So when K, Q, R, everything is same, naturally magnitude of electric field at all such points would be same. And because E value is constant for all these points on the spherical surface, then E can be taken out of the symbol of integration. That's why I am taking it out. But what is left inside now? Integration dA, correct? Now this E as it is, but integration dA means what? Summation of areas of all the area elements. The way you have taken one area element here, you can select such area elements over the entire spherical surface. And again when you add up their areas, you will get total surface area of entire sphere. And for a sphere, don't you know the surface area formula? 4 pi r square, 4 pi into radius square, 4 pi into radius square, correct? Now this phi as it is. What about magnitude of electric field produced by a point charge? By formula KQ upon r square, KQ upon r square. This 4 pi r square as it is, okay? Now r square will cancel. This Q I have written here, 4 pi I have written here. What about small k? Come on, for SI unit system and for vacuum, what was the expression for small k? 1 upon 4 pi epsilon 0. K is 1 upon 4 pi epsilon 0. And now 4 pi will cancel, giving you phi equals to Q upon epsilon 0. Phi equals to Q upon epsilon 0. Okay, fine. Now this is the electric flux linked with this closed surface, okay? And what is this small q? It is a charge inside that closed surface, or you can say it is a charge enclosed by the closed surface. At present it is only a single charge, so I am writing here only q divided by epsilon 0 is permittivity of vacuum, correct? Because surrounding medium we have considered to be vacuum. Instead of vacuum, if this charge is present in other medium other than vacuum, then you must write permittivity of that medium here, okay? This very result itself is known as Gauss law or Gauss theorem for static electricity. Fine. Now here is a single charge, so I am writing only q, but not necessary that inside this closed surface there should be only single charge every time, not necessary. There may be more than one charges. If it is so, then in that case you must take algebraic summation of charges enclosed by closed surface. So at that time instead of q, you must write now sigma q, correct? Epsilon 0 as it is, correct? This gives you more general formula for stating Gauss law, correct? This is most general form of Gauss law for static electricity. From this, if you would like to give the statement, we can give it this way. Look, total electric flux linked with any closed surface is always equal to ratio of algebraic summation of charges enclosed by that closed surface to the permittivity of vacuum, full stop. This very statement is called Gauss law for static electricity. I repeat, total electric flux linked with any closed surface is always equal to ratio of algebraic summation of charges enclosed by that closed surface to the permittivity of vacuum, full stop. This very statement is called Gauss law for static electricity. Got it? Fine. Once again, let me remind, if charge is present in some other medium other than vacuum, then its permittivity you must write here. Okay. Now let us see some noteworthy points regarding Gauss theorem. First point about Gaussian surface. A chargeless closed surface enclosing given charge is called Gaussian surface for that charge. A chargeless closed surface enclosing a given charge is called Gaussian surface for that charge. Just make a note of 3 points here. First, this surface is closed surface. Second, it is chargeless. On this surface itself there is no charge. Here there is no charge. Okay? And third, it encloses some charge. Okay? A chargeless closed surface enclosing some charge is called Gaussian surface for that charge. Fine. Second thing, whether you take here spherical shape or any other shape of closed surface, it will do no problem, because the electric flux link with this surface, it does not depend on radius of this spherical surface, it does not depend on shape, it does not depend on volume. Whether you take this spherical surface or you take any other surface with any other shape, any other volume, no problem, as long as the charge enclosed by the closed surface remains same, then this Q is remaining same and epsilon 0 is as such constant only. So every time you will get same value of electric flux. I mean to say, electric flux linked with any closed surface does not depend on size and shape of the Gaussian surface. It does not depend on the size and shape of the surface. Size means volume. Size means volume. Okay? So electric flux linked with a closed surface does not depend on the shape and volume of the Gaussian surface. Got it? What about sigma q? As I said, it is algebraic summation of charges enclosed by given closed surface. Suppose given closed surface is like this. Look here. You must have seen the children playing with rubber balloon, correct? Sometimes that rubber balloon has this sort of shape, and that rubber balloon has closed surface. It has to have closed surface only, otherwise the gas will leak out. So in that rubber balloon the surface is closed and it is 3-dimensional, it encloses some volume, it is a closed surface. What is the difference between open surface and closed surface? I am showing you. You can take this as open surface. This is an open surface, but it is the lid for this box, and when I make it fitted, now this box you can see it has closed surface, correct? This inside objects are enclosed from all the sides, correct? So this box has closed surface. What is the difference from geometry point of view? Difference is that open surface has only area, open surface has only area, whereas closed surface has volume also. Open surface has only area, whereas closed surface has volume also. This is the difference. Okay, fine. Then this is closed surface. It traps some volume. That's why it has to be 3-dimensional. I am just showing this surface 3-dimensional by such a circle. Okay, it shows the circumference of this circular part. Okay, I just want to show the depth, that's why I am showing it like this. Okay, now consider 7 point charges. How many? 7. Say Q1, Q2, Q3, Q4, Q5, Q6, Q7. Now out of these 7 charges, tell me how many charges are inside this closed surface. How many? 1, 2, 3, 4. But which are they? They are Q2, Q3, Q5 and Q7. And in Gauss law, in the numerator on the right hand side, there is a sigma q which is algebraic summation of charges enclosed by the closed surface, and they are Q2, Q3, Q5 and Q7, and that is why I am making addition like this, Q2 plus Q3 plus Q5 plus Q7, correct. There may be charges outside the closed surface, but here for finding sigma q, you should not consider them, because here is algebraic summation of only those charges which are inside, which are enclosed by the closed surface. Okay, fine. Now here when it is algebraic summation, if charge is positive, you can retain the positive sign, but if charge is negative, then you must write here minus sign. Got it? What about electric flux general expression? We have obtained just now, phi equals to integration vector E dot vector dA. So this electric flux is nothing but integration of vector E dot vector dA. But while finding this electric field, remember all these charges, they contribute in producing resultant electric field. Whether charge is outside the Gaussian surface or inside the Gaussian surface, irrespective of that, remember each charge definitely contributes in forming the resultant electric field. So while calculating this electric flux on the left hand side, you are supposed to consider this formula in which electric field is produced by all the charges. That is why on the left hand side, while finding this electric flux, we must consider the presence of all the charges. But on right hand side in the numerator, while finding sigma q, we should consider only those charges which are enclosed by the Gaussian surface. Okay. What is the physical importance of Gauss law? Physical importance of Gauss law is that using Gauss law, you can find out electric fields produced by some symmetric charge distributions very easily. This is the physical importance. What do you mean by symmetric charge distributions? Symmetric charge distributions are those which have symmetry regarding directions point of view, regarding sides point of view. Okay? Suppose you are talking about, say, a line made up of point charges. You are talking about a plane made up of point charges. You are talking about spherical shell made up of point charges. You are talking about a sphere made up of point charges, like that. These are symmetrical charge distributions, and electric fields produced by them can be found out by using Gauss law very easily. This fact gives you its physical importance. Okay.